Hey everyone, thank you, Amir. So my name is Mehdi Khanzadeh. I'm an associate professor at Temple University. I'm gonna basically give you some example from application of neutron and X-ray imaging. It's kind of combination of my own PhD stuff as well as my PhD student that recently graduated. So on the neutron imaging part, the topic I'm going to discuss is the internal curing, mainly quantifying the curing affected zone and how the implementation of the internal curing can impact the duration of external curing. For example, if I have internal curing, can I reduce the duration of external curing by a certain percentage? We don't have that answer, so we're trying to answer that by using the neutron imaging. The second part is micro XRF or X-ray fluorescence. We use it for chloride profile evaluation, and based on that high spatial resolution, we're able to basically look at a lot of features inside the sample, such as the cracking or impact from the sealers, curing methods, and so on. Starting with the neutron imaging. So for those of you that not familiar with the internal curing, this is just a very short background on it. So we use the lightweight aggregates, so they have a higher porosity, as you can see on the top image, to store the water. So later on, after the setting time, they're going to dissolve water to the matrix to internally cure your system versus that external curing that has a limited depth, okay? So that's the advantage of basically internal curing. You have better distribution, as you can see at the bottom cartoons. So for the first part, again, objective was to see how implementation of internal curing going to impact the external curing duration. We know it impacts the performance, improves the internally the performance. But how about the construction practices? Because this could be again, benefit. We can sell this new technology and convince the contractor to use it if there's a reduction in the curing duration. So for this purpose, we casted 8 different mixtures. We had 2 different water binder ratios. We had system with the fly ash, system with the silica fume. So after casting, we sealed the sides and the bottom, and we just basically cured it from the top. So we had a different curing method. So again, some of the samples were internal cured, some of them were not. And from the top, we used the wet bare lab for wet curing, so for different durations. And at 28 days, we started testing them, basically preparing the sample for testing. And in some cases, we applied the curing compounds, 2 different types of the curing compound that I'm going to discuss later on, how they basically perform compared to the wet curing. So we take these slices for different testing. We're going to focus on the neutron imaging. So we have these slices about 20 millimeter thickness for our testing. So the background on neutron imaging, so we use this facility at Oregon State University. So basically you have, if you look at this, you have a neutron beam coming and passing through the sample. Part of that neutron is going to attenuate it, and part of that is going to capture by detector, right? So difference between that initial intensity and the final intensity you have in the detector can give us an indication about a lot of stuff. One is the thickness of the materials that impacts the other, attenuation coefficient of the material. So the good thing about the neutron, other than being a high resolution for a spatial, again, characterization, was good interaction with the hydrogen atoms, right? So we can track the water distribution using the neutron, while that's not the case with the X-ray, okay? So again, by using this Beer-Lambert law, we can quantify what is that attenuation, and we can, again, quantify the absorption in the concrete. We can quantify drying phenomena in the concrete and different, basically, durability issues and so on. But in this study, we were interested in the degree of hydration, basically the amount of chemically bound water due to the curing, because that can give us an indication how different curing methods we are applying is going to impact the profile of your degree of hydration. So this is an example you are seeing here, the neutron image from our cross-section. So that's the top surface, and over the depths, we can get what we call volume of non-evaporable water or chemically bound water. Basically, that's indication of our degree of hydration. So you see at the surface, this is my surface. I have low volume, right? And as I go into the depths of the system or sample, there is a uniform, okay? So by using that, I'm going to later discuss how we quantify that curing affected zone. And then based on that, how I can correlate the internal cured versus not internal cured system or any other curing techniques that I'm using. So this is more about how we quantify this. Basically, we say if we oven dry our system after we prepare the samples, we get rid of all the free water in the system, in the pores. The only water left is the bond water, okay? So we can, again, expand the Beers-Lambert law, and we can quantify that volume of non-evaporable water over the depths of the sample. We expanded to the SEM system because, as I said, we had fly ash and also silica fume in our study. So the same formula, we just included the SEM, basically the Poznanic reaction effect there. So these are some example profiles. So at the left side, you are seeing the not internal cure system, water binder 0.45. At the right side, you are seeing the internal cure one. So if you look at the left side, just the impact from the duration of the wet bare lab curing. If you look at the surface, you see that impact, right? When we are extending the curing period, we get better performance, or the surface is as similar as the bulk of your sample, or even when you extend it, it's going to be better. It's not surprising, we know this, but the point is quantification of this, right? How we can exactly quantify this. If you look at the impact from the internal curing, you see at the surface, we reduce that gradient or the curing affected zone. Later on, I'm going to say how we quantify that. And also, we impact the bulk of the sample. We improve the degree of hydration at the bulk of the sample. So we wanted to get a more quantification to have just that equivalency line between an internal cured and non-internal cured. So we took those profiles, and then we defined this area as a curing affected zone, basically from the surface to the point that you reach to that bulk uniform degree of hydration, okay? So we call that curing affected zone, and based on that curing affected zone, we can find for different curing times, and we can plot it for the virgin mix versus the internal cure mix, okay? So we can do it for different mix design. After this point, we want to basically find that equivalency line. As I mentioned at the beginning, if the requirement is 5 days for the virgin system, by using this profile, I can find what is the requirement for internal cure one, right? So for different points, I can find that data point. And then here at the right side, I have external curing without IC, internal cure, and with IC. So based on those data points, I can find that equivalency line, right? So that's basically the reduction in the curing time because of use of the internal curing, right? So we have that percentage of the reduction in the required external curing period. So based on our study, we see about 50 to 60% reduction in the duration of the external curing. They use the internal curing. Right now, one of the DOTs, the New York DOT, actually applying this. Their specification was 14 days wet curing for their bridge decks. but they require internal curing, and they reduce the external curing to 7 days. So that saves a lot of, again, construction time, a lot of cost, and also from the safety aspect is improvement. So we looked at the impact from the curing compounds. We tested 2 different curing compounds here. One is a resin-based, the other one PAMS-based. So in case of the resin-based, again, we quantified that curing affected zone. Resin-based is similar to 1-day wet curing, while PAM-based is similar to at least 7 days of the wet curing. So again, this technique gives us that ability to test any new materials, any new techniques, and see the benefits or quantify if they are working or not, right? So again, we can do that for curing compound or different type of the curing compound. So these are some conclusions for the first part for neutron imaging. So as I said, we see a lot of reduction in curing affected zone by use of the internal curing. That's about 50 to 60% in duration of external curing. And the other basically conclusion we can have is basically the importance of the techniques such as the neutron imaging to help us understand the impact from new technologies in our field. The second part, the X-ray imaging, as I said, I'm going to more focus on the micro X-ray fluorescence. So it's a similar technique as bulk XRF. The difference is we have this polycapillary optic to get to about 50 micron diameter resolution. Okay, so this is an example of the technique or the machine we use. So the type of the data we get from this technique is, other than a spectrum, we can get the elemental maps. Okay, so similar to SEM technique, but the good thing about the micro XRF, I can use it for 4 by 4 inch basically samples, large samples, with the very low preparation needed. Okay, so that's an advantage compared to SEM. So when we get this elemental map, we develop this process, image processing method to basically develop this compositional map. So we basically extract all those elemental maps, combine them, and then we have this compositional map. Okay, and then we can extract the aggregate from the paste. So whatever study we do on the paste part, so we can exactly say what is the based on percentage or weight percentage of the paste rather than the entire concrete, which was the case in coloride profiles. So here's the example for coloride profile, basically the evaluation. So we have this sample, so we analyze, we cut slices over the depths, and with 50 micron resolution, we can get these coloride counts here, right? So without aggregate and with aggregate, we can have, again, different coloride counts based on the percentage. Then using standards, we can move from the coloride counts to coloride concentration profile with high accuracy. And we basically tested multiple samples, about 20 samples, and we compared with the result from the titration, and the results were comparable to confirm the validity of our method. So what is the application really, other than getting a high resolution data, is to look at some of the, again, features in our sample, especially when the sample comes from the field, to see what is going to be the impact, right? For example, here we have, we received a concrete core from Oklahoma DOT. This is, I believe, extracted right next to the expansion joint. They've seen a lot of crack. So we looked at this, and as you can see here, we have wider crack versus narrower crack. When we have a wider crack, the concentration of the coloride is the same as the concentration of the coloride at the top of your sample, okay? So again, this can help us to understand the impact from the cracks and how that's going to change the coloride concentration over the depths and quantifying that. The other example we had is impact from the sealers. So there is a new type of the sealer. The DOT wanted to adopt it. So it was a combination of the silane plus epoxy versus the just the silane. And we had a control system. So we tested this 3 different systems after applying silane and drying period for chloride penetration. So this is a quantification, basically. So we saw that the system with silane epoxy, new system, after even 90 days of the ponding, there's no chloride penetration in the system. In just the silane, we have a little bit of the penetration, and compared to control, it's much higher, right? So again, we can quantify it. We can look at the performance of the different new materials that they want to specify for their different projects. And one interesting observation we had is not just the difference was not just the epoxy addition. The type of the silane they used previously was different than the new type of the silane. In the previous one, they had 40% solid content, and the new one is almost 100%. So that gave us basically more penetration as far as the depth of the silane. Okay, so that's another observation we had in this case. The last example I have in this case is the impact from the curing methods. So there was a lot of controversy on the use of the lithium silicate curing compounds. So they come up to us, and then we went to basically core different samples from the bridge decks. 2 span of the bridge deck were wet cured, and 1 span was lithium cured. Basically, they used the lithium silicate curing compound. So we brought that samples to the lab. We ponded with the chloride solution, and after a certain period, we tested them. So the blue one is the wet curing. The other one is the orangish color is the basically lithium silicate. So that was our observation. Basically, lithium silicate was performing worse than the wet curing. Okay, so because they were planning to apply this. It was cheaper, so they were planning to apply this on all the bridge decks. So this study kind of stopped that for. So again, before we go use the new system, we can use this technique to exactly understand what's going on with or how they impact in our performance. At the end, I would like to acknowledge the funding sources for the first part of the study I shared on the internal curing. And with that, thank you for your attention, and I'm happy to answer any questions.